Well, hello and welcome to the third Thursday webinar. I am Tom Sandry, and this is actually our last third Thursday webinar for the calendar year of 2022. Today, we're going to be talking about benefits of battery testing, specifically taking a look at internal ohmic trending of battery units and battery cells. So, let's get started. Now, before we get into the ohmic trending, let's first review failure modes and the causes of failures in batteries. Now, the operation of batteries at elevated temperature will result in increased positive plate grid corrosion or oxidation. And in extreme cases, it can bring about oxidation of the bus bars in the battery. Now, positive grid corrosion is a normal end-of-life failure mode of batteries, which is greatly accelerated at elevated operating temperatures. Grid corrosion will cause the plates to grow. Now, a certain amount of plate growth is designed into batteries and into battery containers or jars. Grid corrosion is commonly accelerated due to overcharging of the battery, excessive cycling, and obviously excessive temperature. Now, if you are conducting an internal ohmic test on the cell or the unit, positive plate grid corrosion will cause an increase in the internal ohmic value. All right, next let's look at hydration. Now, lead dissolves in water. If a lead acid or lead calcium cell is discharged and is not recharged properly, lead can dissolve within the water and the electrolyte. For this to occur, the discharge would have to be fairly deep. For example, the specific gravity reaches a point of 1.05 or less. The solubility of lead increases notably as the electrolyte contains a larger percentage of water. This process is referred to as hydration, and the compounds formed are referred to as lead hydrate. The lead hydrate deposits on the plates and passes through the retainers and separators, causing thousands of short circuits between the plates. While hydration occurs, a white milky substance appears on the plate edges and the transparent jar. A battery in this state should be replaced. Now, again, if we're conducting an internal ohmic test, hydration will cause the lowering of the internal ohmic values. Next, plate sulfation. Plate sulfation is similar in appearance to hydration. It is caused by the formation of lead sulfate crystals on the plates. Normally, this is a result of an inadequate float charge or by leaving float voltage off. This problem can be corrected in many cases by performing an equalization charge. Now, sulfation is an important consideration during storage of cells. As cells sit in storage and they self-discharge, the active materials of the electrodes convert to lead sulfate just as they do in other discharges. In self-discharge, the lead sulfate forms a larger crystal that have the effect of insulating the particles of the active material, either from each other or the grid. Now, since lead sulfate occupies more space than sponge lead, the negative plate expands in volume. If the cell is allowed to over-discharge, the lead sulfate may expand to the point where it separates from the sponge lead and falls to the bottom of the jar as sediment, which leads us to sediment and shedding. Sediment or shedding are small deposits at the bottom of the jar. Now, a small amount is normal and it is part of the aging process. As the sediment builds, it can cause plate shorts. Now, shedding is caused by overcharging, undercharging, excessive cycling, and temperature. Undercharging will cause sulfation slew-off. Overcharging will result in positive grid growth, active material and gases. All right, now let's take a look at hard shorts. Hard shorts can occur in flooded cells and valve-regulated lead-acid cells. The hard short is basically a short circuit between two adjacent plates, and it is caused by a paste lump not being removed during the manufacturing process. Now, typically, if a paste lump is present early in the battery's life, the paste lump will push its way through the separator and contact the opposite polarity plate. The hard short initially will show up as a decrease in the internal ohmic value of the battery and eventually as a lower float voltage. Next, let's look at dryout, or loss of compression. Dryout is a catastrophic failure mode that can occur in valve-regulated lead-acid batteries. VRLA batteries cannot replace lost water. AGM separators become undersaturated and lose contact with plates. Excessive heat causes jar walls to bulge. This physical deformation causes separator and plates to lose compression. Gel cell electrolyte dries and cracks, losing contact. Now, if ohmic trending is performed, dryout can be detected by an increase in internal ohmic value. Dryout is commonly caused by overcharging and elevated temperatures. Post-leakage. Post-leakage is the seeping or leaking of electrolyte from around the battery posts. Post-leakage is unsightly and it should be cleaned as found. Post-leakage left in place can lead to post-corrosion, which then can lead to a cracked cover or jar. Now, visual inspections will show signs of possible post-leakage in flooded cells. However, this could be due to a spill on top of the battery. This is another reason why it's best to keep batteries clean. If someone cleaned the spill directly after the spill occurred and you do see moisture or seepage, now at this point you can be sure that it is in fact post-leakage and not a spill. All right, thermal runaway. Thermal runaway is a condition that occurs in a battery, especially valve-regulated types, when charging energy results in heat generation within the battery greater than the heat dissipated, causing an uncontrolled rise in battery temperature. This can cause failure through cell dryout, shortened life, and or melting of the battery. Once started, thermal runaway is self-sustaining. It can end in complete and catastrophic failure. Flooded cells allow gas to escape where valve-regulated lead acid recombines oxygen and forms water. The recombination of oxygen at the negative plate in a valve-regulated lead acid battery is a chemical reaction which produces heat during the recharge process. Thermal runaway can be caused by overcharging, high ambient temperature, low airflow, or high float voltage. Now, internal ohmic values will increase, as will float current, before thermal runaway occurs. All right, next let's look at loose connections. Loose intercell connections are frequently a problem with all types of battery systems, however, are easily found through a low resistance measurement across each strap. A loose connection translates to high resistance, and when the system is called upon to serve the load, the high resistance connection will have a temperature related to the watts lost, where watts lost is equal to the I squared R. Now, the problem with the elevated resistance and temperature is that they tend to feed each other. As the temperature of the metals in the strap and post increase, the resistance increases, which causes the temperature to rise, and the cycle begins. At high enough temperatures, the lead post on the battery can melt, causing failure of the string and, obviously, serious damage. All right, now let's take a look at temperature. The internal chemical reaction in any battery will begin to slow down as temperature decreases. The degrees of reduced performance will vary according to the battery technology. For example, at temperatures nearing freezing, a valve-regulated lead-acid may need capacity compensation of 20%. Lead-calcium cells using 1.215 specific gravity will require a doubling of capacity, while a NiCad will need about 18% increased capacity. Now, at the other end of the range, high temperature is the killer of all batteries. Once again, the degree will vary according to the battery technology. Lead acid at 95 degrees Fahrenheit will experience a 50% shortened life, while NiCad will experience a 16 to 18% shortened life. By applying what Swedish scientist Arrhenius learned regarding chemical reactions, we see that for every 18 degree Fahrenheit increase in battery temperature, the battery life is halved. The increased temperature causes faster positive grid corrosion as well as other failure modes. By holding a lead-acid battery at 95 degrees Fahrenheit instead of its designed 77 degrees Fahrenheit, a 20-year battery will last only 10 years, a 10-year battery only 5 years, and so on. Increase the temperature yet another 18 degrees Fahrenheit up to 113 degrees Fahrenheit, and a 20-year battery will last only 5 years. Now, a battery is rarely held at a temperature for its entire life. A more realistic scenario is for a battery to heat during the day and cool down during the night, with higher average temperatures in the summer and lower average temperatures in the winter. Now, unfortunately, cooling the battery off to 77 degrees Fahrenheit will not gain back the life that was lost at the elevated temperature. Once the positive grid corrosion begins, it cannot convert back again. Furthermore, positive grid corrosion occurs at all temperatures. It is merely the speed of the corrosion rate. The result is to control as best as possible the temperature of the batteries in the network. Now let's take a look at test and inspection. It is important to understand that no single test tells the whole story. The purpose of testing is to determine what the condition of the batteries are in, and hopefully give some idea where this condition is headed and possibly how fast. You do not want to find out during a power outage that the batteries did not have sufficient capacity and your load was dropped sooner than designed, or that the entire system failed due to a single component failure, and that all of this could have been predicted and prevented. Because of this, it is always best to have as much test data as possible and be sure to record the data. Now, what are cell or unit internal ohmic measurements? Well, with the introduction of valve-regulated lead-acid or VRLA batteries to station DC supplies in the 1980s, several of the standard maintenance tools that are used on vented lead-acid or VLA batteries were unable to be used on this new type of lead-acid battery in order to determine its state of health. The only tools that were available to give indication of the health of these new VRLA batteries were voltage readings of the total battery voltage or the voltage of the individual cell, and also periodic discharge tests. Now, in the search for a tool for determining the health of a VRLA battery, several manufacturers studied the electrical model of a lead-acid battery's current path through its cell. The overall battery current path consists of resistance and inductance and capacitive reactance. The inductive reactance in the current path through the battery is so minuscule when compared to the huge capacitive reactance of the cell that it is often ignored in most circuit models of the battery cell. Taking the basic model of a battery cell, manufacturers of battery test equipment have developed and are marketing testing devices to take measurements of the current path in order to detect degradation in the internal path through the cell. Now, in the battery industry, these various types of measurements are referred to as ohmic measurements. Terms used by the industry to describe ohmic measurements are AC conductance, AC impedance, and DC resistance. They are defined by the test equipment providers and IEEE and refer to the method of taking ohmic measurements of lead-acid batteries. For example, in one manufacturer's AC conductance equipment, measurements are taken by applying a voltage of a known frequency and amplitude across a cell or battery unit and observing the AC current flow it produces in response to the voltage. Now, a manufacturer of an AC impedance meter measures AC current of a known frequency and amplitude that is passed through the whole battery string and determines the impedance of each cell or unit by measuring the resultant AC voltage drop across them. On the other hand, DC resistance of a cell is measured by a third manufacturer's equipment by applying a DC load across the cell or unit and measuring the step change in both the voltage and current to calculate the internal DC resistance of the cell or the unit. Now, it is important to note that because of the rapid development of the market for ohmic measurement devices, there were no standards developed or used to mandate the test signals used in making ohmic measurements. Manufacturers using proprietary methods and applying different frequencies and magnitudes for their signals have developed a diversity of measurement devices. This diversity in test signals, coupled with the three different types of ohmic measurement techniques, impedance, conductance, and/or resistance, make it impossible to always get the same ohmic measurement for a cell with different ohmic measurement devices. However, IEEE has recognized the great value for choosing one device for ohmic measurement, no matter who makes it or the method to calculate the ohmic measurement. The only caution given by IEEE and the battery manufacturers is that when trending the cells of a battery, consistent ohmic measurement devices should be used to establish the baseline measurement and to trend the battery set for its entire life. Now, for valve-regulated lead-acid batteries, both IEEE Standard 1188, maintenance testing and replacement of VRLA batteries, and IEEE Standard 1187, installation design and installation of valve-regulated lead-acid batteries, recognize the importance of maintenance activity of establishing a baseline for a cell unit internal ohmic measurements, impedance, conductance, and/or resistance, and trending them at frequent intervals over the life of the battery. There are extensive discussions about the need for taking these measurements in these standards. IEEE Standard 1188 requires taking internal ohmic values as described in its Annex C4 during regular inspection of the station battery. For valve-regulated lead-acid batteries, IEEE Standard 1188, in talking about the necessity of establishing a baseline and trending it over time, it says, depending on the degree of change, a performance test, cell replacement, or other corrective action may be necessary. And this quote can be found in the IEEE 1188-2005 in the Appendix C section. Now, for vented lead-acid batteries, IEEE Standard 450, maintenance testing and replacement of VRLA batteries, and IEEE Standard 484, installation of VRLA batteries, give several guidelines about establishing baseline measurements on newly installed lead-acid stationary batteries. The standards also discuss the need to look for significant changes in the ohmic measurements. The caution that measurement data will differ with each type of model of instrument used, and it also lists several factors that affect ohmic measurements. Now, since the introduction of ohmic measurements back in 1987, there have been numerous industry papers, white papers from leading domestic battery manufacturers, and others for addressing ohmic measurement testing, plus 4 Electrical Power Research Institute or EPRI studies to determine the relationship of internal ohmic measurements to the capacity of a lead-acid battery cell. The studies indicate that internal ohmic measurements were in fact a good indicator of a lead-acid battery cell's capacity. But because users were often interested in the total station battery capacity, and the technology of ohmic trending does not precisely predict overall battery capacity, if a user needs an accurate measure of the overall battery capacity, they then should perform a battery capacity test. Now, prior to the EPRI studies, some large and small companies which owned and maintained station DC supplies developed maintenance programs where trending of ohmic measurements of the cells or units of the station battery became the maintenance activity for determining if the station battery could perform as manufactured. By evaluation of the trending of ohmic measurements over time, the owners could track the performance of the individual components of the station battery and determine if a total station battery or components of it require capacity testing, removal, replacement, or in many instances, replacement of the entire station battery. By taking this condition-based approach, these owners have eliminated having to perform capacity testing at prescribed intervals to determine if a battery needs to be replaced, and are still able to effectively determine if a station battery can perform as manufactured. Now, analyzing cell or unit internal ohmic data. Cell unit internal ohmic data can help give us an indication of the overall state of health of an individual cell or unit against the rest of those in the battery bank. It can also be used to determine where on the overall life cycle the battery cell resides, and it can give us an indication of how quickly a battery is beginning to age. By measuring all the individual cell or unit internal ohmic values within a battery string and then calculating the average ohmic value for the entire bank, we can identify possible problematic cell or units before they get to the point where they pull down the performance of healthy cells and units. For lead-acid cells, we would like to see each cell fall within plus or minus 10% of the average ohmic value. When a cell reaches a deviation of 15%, we want to conduct further investigation of that individual cell. If a cell falls plus or minus 20%, we want to put a warning on that cell and possibly perform a single cell discharge. Now, if baseline data is available, we can compare a cell's internal ohmic value to the expected ohmic value of a cell of that particular type and brand, which leads us to the establishment of baselines. Establishment of a cell or unit's internal ohmic baseline measurements should be completed when lead-acid batteries are newly installed. To ensure that the baseline ohmic values are most indicative of the station battery's ability to perform as manufactured, they should be made at some point in time after the installation to allow the cell chemistry to stabilize after the initial freshening charge. An accepted industry practice for establishing baseline values is after 6 months of installation, with the battery fully charged and in service. However, it is recommended that each owner, when establishing a baseline, should consult the battery manufacturer for specific instructions on establishing an ohmic baseline for their product, if available. Now, when internal ohmic measurements are taken, the same make and model test equipment should be used to establish the baseline and used for future trending of the cell's internal ohmic measurements because of variances in test equipment and the type of ohmic measurement used by different manufacturers' equipment. Keep in mind that one manufacturer's conductance test equipment does not produce similar results to another manufacturer's impedance test equipment, even though both manufacturers produce ohmic test equipment. Therefore, for meaningful results to an established baseline, the same make and model of instrument should be used. Now, for all new installations of valve-regulated lead-acid batteries and vented lead-acid batteries, where trending of the cell's internal ohmic measurement to a baseline are to be used to determine the ability of the station battery to perform as manufactured, the establishment of the baseline, as described earlier, should be followed at the time of installation to ensure the most accurate trending of the cell or unit. However, often for older VRLA batteries, the owner of the station batteries have not established a baseline at installation. Also, for owners of VLA batteries who want to establish a maintenance activity which requires trending of measured ohmic values to a baseline, there was typically no baseline established at installation of the station battery in order to trend to. So, to resolve the problem of the unavailability of baseline internal ohmic measurements for the individual cell or units of a station battery, many manufacturers of internal ohmic measurement devices have established libraries of baseline values for VRLA and VLA batteries using their testing devices. Also, several of the battery manufacturers have libraries of baselines for their products that can be used to trend to. However, it is important that when using battery manufacturer supplied data, that it is verified that the baseline readings to be used were taken with the same ohmic testing device that will be used for future measurements. Again, conductance readings from one manufacturer's test equipment do not correlate to impedance or possibly resistance readings from a different manufacturer's test equipment. Now, although many manufacturers may have provided baseline values, which will allow trending of the internal ohmic measurements over the remaining life of a station battery, these baselines are not the actual cell or unit measurements for the battery being trended. It is important to have a baseline tailored to the station battery to more accurately use the tool of ohmic measurement trending. That more customized baseline can only be created by following the establishment of a baseline for each of the cells at the time of installation of the station battery. All right, now throughout this webinar thus far, we've been really focusing a lot on the lead-acid style batteries. So what are the differences between lead-acid and nickel-cadmium? Well, there is a marked difference in the aging process of lead-acid and nickel-cadmium station batteries. The difference in the aging process of these two types of batteries is chiefly due to the electrochemical process of the battery type. Aging and eventual failure of lead-acid batteries is due to expansion and corrosion of the positive grid structure, loss of positive plate active material, and loss of capacity caused by physical changes in the active material of the positive plates. In contrast, the primary failure of nickel-cadmium batteries is due to the gradual linear aging of the active materials in the plates. The electrolyte of the nickel-cadmium battery only facilitates the chemical reaction. It functions only to transfer ions between the positive and negative plates, but is not chemically altered during the process like the electrolyte of a lead-acid battery. A lead-acid battery experiences continued corrosion of the positive plate and grid structure throughout its operational life, while a NiCad battery does not. Changes to the properties of a lead-acid battery when periodically measured and trended to a baseline can indicate aging of the grid structure, positive plate deterioration, or changes in the active materials in the plate. Because of the clear differences in the aging process of lead-acid and nickel-cadmium batteries, there are no significantly measurable properties of the NiCad battery that can be measured at a periodic interval and trended to determine aging. All right, next, let's take a look at some regulatory agencies. The National Electrical Reliability Corporation, or NERC, is a nonprofit corporation. Their main mission is to ensure the reliability of the bulk power system in North America. The Federal Electric Reliability Commission, or FERC, is a U.S. government regulatory agency. Among FERC's many responsibilities is the regulation of the interstate transmission of electricity. Now note, the term bulk electrical system, or BES, and bulk power system, or BPS, essentially mean the same thing in context and are used interchangeably in this webinar. Now, a little bit of background and history. On August 14th of 2003, at about 4:10 p.m. Eastern Daylight Time, 50 million people lost power in the northeastern and midwestern United States, as well as Ontario, Canada. This was the second major blackout in post-war America, the first one occurring on November 9th of 1965. That one took out the whole Northeast as well. As a result, Congress passed the U.S. Energy Act in 2005, better known as the Electric Modernization Act of 2005. This act authorized FERC to designate an Electric Reliability Organization, or ERO, by which NERC became the franchise owner of its role for the bulk power system. The ERO designation authorizes NERC to create and enforce standards upon the suppliers to the bulk power system. Now, let's talk about some definitions. FERC's Modified Bulk Electric System, or BES, definition is composed of two parts. A core definition that establishes a bright line threshold that includes all facilities operated at or above 100 kV, and a list of configurations that are deemed to be, regardless of their voltage rating, included or excluded from the bulk electric system. Facilities that are deemed to be included in the bulk electric system are subject to compliance with NERC reliability standards. Now, on July 19, 2007, FERC issued Order 693 that mandated 83 NERC reliability standards be established and implemented. PRC 005 was one of those 83 standards. At that time, a glossary of definitions was established that defined reliability as ensuring that the bulk power system is able to meet the electricity needs of all end user customers, even when unexpected equipment failures reduce the amount of available electricity. So let's take a look at the existing NERC standards for protection system maintenance and testing. For critical bulk electrical system protection functions, NERC standards have required that each utility or asset owner define a testing program. The starting point is the board-approved standard PRC 005-5, briefly restated as follows. The purpose: to document and implement programs for the maintenance of all protection systems affecting the reliability of the bulk electrical system so that these protection systems are kept in working order. So let's look at definition of protection system. The most recent approved definition of a protection system is protective relays which respond to electrical quantities, communication systems necessary for correct operation of protective functions, voltage and current sensing devices providing input to protective relays, station DC supply associated with protective functions, including station batteries, battery chargers, and non-battery based DC supply. And finally, control circuitry associated with protective functions through the trip coil or coils of the circuit breakers or other interrupting devices. Now, in addition to verifying the circuitry that supplies DC to the protection system, the owner must maintain the station DC supply. The most widespread station DC supply is the station battery and charger. Unlike most protection system components, physical inspection of the station battery for signs of component failure, reduced performance, and degradation are required to ensure that the station battery is reliable enough to deliver DC power when required. Now, IEEE standards 450, 1188, and 1106 for vented lead acid, valve-regulated lead acid, and nickel-cadmium batteries, respectively, which are the most used station batteries on the NERC bulk electrical system, have been developed as an important reference source of maintenance recommendations. The protection system owner might want to follow the guidelines in the applicable IEEE recommended practices for battery maintenance and testing, especially if the battery in question is used for application requirements in addition to the protection and control demands covered under the standard, or the standard PRC 005 that we're talking about. However, the standard drafting team has tailored the battery maintenance and testing guidelines in PRC 005 for the protection system owner, which are application specific for the bulk electrical system facilities. While the IEEE recommendations are all-encompassing, PRC 005 is a more economical approach while addressing the reliability requirements of the bulk electrical system. Now, let's take a look at the tables that appear in the PRC 005. Table, for instance, 1-4A. This is for protection system station DC supplies using vented lead acid or VRLA batteries. Now here we see under maximum interval, every 4 calendar months we are to, as far as our activities, verify station DC supply voltage and inspect electrolyte levels and inspect for unintentional grounds. Every 18 calendar months, our activities are to verify float voltage of battery charger, battery terminal connection resistance, battery intercell or unit-to-unit connection resistance. Also, every 18 calendar months, we are to inspect the cell condition of all individual battery cells where the cells are visible, or measure battery cell or unit internal ohmic values where the cells are not visible. So here we see ohmic measurements showing up in the NERC PRC 005 under maintenance activities. Also, under that 18 calendar months, we are to inspect physical condition of the battery rack itself. Now, Table 1-4A continued. We also see that every 18 calendar months, we are to verify that the station battery can perform as manufactured by evaluating the cell or unit measurements indicative of battery performance. And they give example again here being internal ohmic values or float current, and to compare this against the station battery's baseline. Now, very interesting, in this 18-month, we can either follow the interval of every 18 months and do those ohmic measurements or float currents, or every 6 calendar years, we would need to verify the station battery can perform as manufactured by conducting a performance or modified performance capacity test on the entire bank. So very interesting in the tables. We see a OR statement where every 18 months, for instance, we can do internal ohmic trending, or every 6 calendar years, we would perform capacity or load bank testing. Now, Table 1-4B. Basically, this one very similar, except this one is for valve-regulated lead-acid batteries, or VRLAs. Now again, every 4 calendar months, we are to verify station DC supply and inspect for unintentional grounds. Every 6 calendar months, we inspect the condition of all individual units by measuring the battery or cell or unit's internal ohmic values. So again, every 6 months, we take internal ohmic measurements. Every 18 calendar months, we are to verify float voltage of the battery charger, battery continuity, battery terminal connection resistance, battery intercell or unit-to-unit connection resistance, and every 18 months, we inspect the physical condition of the battery rack itself. Table 1-4B continued. Every 6 calendar months, we verify the station battery can perform as manufactured by evaluating the cell or unit measurements indicative of battery performance. Once again, we see an example being the internal ohmic values or the float currents against the station battery baseline. We once again see, though, this OR statement that either we can follow the every 6 calendar month regime, or every 3 calendar years, we need to verify that the station battery can perform as manufactured by conducting a performance or modified performance capacity test on the entire bank. And now we look at Table 1-4C, which is for the NiCad or nickel-cadmium batteries. Every 4 months, we're to verify station DC supply voltages and inspect electrolyte levels and also inspect for unintentional grounds. Every 18 calendar months, we are to verify float voltage of the battery charger, battery continuity, battery terminal connection resistance, battery intercell or unit-to-unit connection resistance. And every 18 months, we are to inspect cell condition of all individual battery cells and also the physical condition of the battery rack. Table 1-4C continued. Every 6 years, we are to verify that the station battery can perform as manufactured by conducting a performance or modified performance capacity test of the entire bank. Now, as we see in the nickel-cadmium, there is no call out for the internal ohmic trending because, as we discussed earlier, when comparing NiCads to lead-acid batteries, there really are no degradations that can be trended in the NiCad batteries. And that concludes our Third Thursday webinar, our final Third Thursday webinar for the year of 2022. Again, I do truly appreciate your participation in these webinars. For those of you that have been with us all year long and have attended all 12 of the webinars, thank you very, very much. I hope you have been finding value in this program. We here at Protec definitely enjoy doing the Third Thursday webinars, and obviously we are going to continue in 2023. All right, without further ado, how about we get to those questions and answers?